your video. So we can start. So today, Laura will tell us about STROBE-X, revealing fundamental physics via the life cycles of compact objects and the dynamic universe. So Laura obtained her PhD in astronomy from the University of Maryland in 2007. Her dissertation involved the creation of the first publicly available model to measure the black hole spin through the reflection spectroscopy. After a 2-year NASA postdoc fellowship at NASA, Laura joined the CFA as a postdoc, working with Martin Elvis in 2009. She became an SAO staff member in 2014 and currently serves as the Deputy Associate Director for the High Energy Astrophysics Division at the CFA. Her research focuses on understanding how AGN and their supermassive black hole co-evolve through the process of accretion and energetic outflows. And she has leadership roles in several current, planned, and proposed international X-ray missions. So the floor is yours, Laura.
Thanks, Yuri. Hi, everyone. Can everybody hear me okay? Good. Strangely enough, they don't seem to make microphones that clip onto, non-collared shirts, which I know is a hindrance for a lot of people who don't prefer collared shirts at conferences. Anyway, neither here nor there. So today I have the great pleasure to talk about one of the plethora of probe concepts that's being put forth in response to NASA's recent probe AO. This one is STROBE-X, which is not too long-suffering an acronym, the Spectroscopic Time-Resolving Observatory for Broadband Energy X-rays. And this is an observatory whose particular design is to look at the time domain universe. All good? Okay. Except now the slides do not want to advance. Do I need to click on something other than a button?
You may turn off and then come in again because we.
Hold, please. No. Once again. There we are. Okay, so as I was saying, this is an observatory particularly designed to answer one of the central themes of the recent decadal survey, that is new windows on the dynamic universe. So a couple direct quotes that address this theme: higher sensitivity all sky monitoring of the high energy sky, complemented by capabilities in the optical, is a critical part of our vision for the next decade in transient multi-messenger astronomy. Also, it is not an exaggeration to say that nearly daily movies of the sky made across the electromagnetic spectrum are their own form of new messenger, with information that is fundamentally distinct from a static view of the universe. So in order to get these wonderful daily movies of the sky, you need large collecting areas, which we know that the broad landscape of the 2030s is going to provide for us across the multi-messenger and electromagnetic spectrum. And you also need excellent throughput and sensitivity. So just to talk a little bit about how STROBE-X will address all of these themes, this is going to be an observatory that truly probes fundamental physics of compact objects in particular, revealing how they form, how they evolve, and how they eventually die. So the three main science pillars, it's going to uniquely apply multiple methods of measuring black hole spins and masses in particular for both stellar and supermassive black holes. It's going to make precise measurements on the neutron star radii, probing the equation of state of very dense matter. And it's going to monitor the X-ray sky for transients and variability on a wide variety of timescales. So this is going to be an observatory with massive collecting area, excellent throughput and sensitivity, and actually extremely high time resolution as well. The concept is being led by Paul Ray. The probes, as many of you probably know, are going to be PI-led missions. Paul works out of NRL. Deputy PI is Keith Gendreau at Goddard. We also have Colleen Wilson-Hodge on board as the project scientist, and Tom Macarone of Texas Tech leads the over 200-member science working group now. And this is a broadly dispersed and diverse crew of people led by a steering committee, of which I have the pleasure of serving on. So in terms of the provenance of the mission, as most of you know who have worked on missions before, typically concepts get kicked around in one form or another for a while, and occasionally people who had good ideas talk to each other and they wind up merging their concepts. So this is kind of what happened in this case. Paul Ray had this idea for an ACSTAR mid-X concept back in 2007 that basically looked at what RXTE had been able to do across the landscape, looking at transients and a variety of other X-ray phenomena, and said, why don't we do something bigger and better? Then they ultimately teamed up with a concept called LOCKed, which is kicking around in Europe at the time in response to the M3 proposal. It ultimately did not get selected for funding, but a significant amount of development had already taken place. Around the same time, Keith Gendreau was looking at NICER, which of course, I think most of you have been familiar with the science that's been coming out of that. We've had a wonderful Nature paper on some of the science that NICER's done on compact objects recently. Ultimately, Keith wanted to make a souped up version of NICER as well. And it turned out that when three people started talking, there were a lot of synergies to be had between these different concepts in terms of the science they ultimately wanted to address. So STROBE-X was born, consequently. Now, as I was saying, this is an observatory that's going to offer transformational capabilities, primarily in collecting area. A good analogy to think of, if you're an optical person, is going from something like the Keck telescopes to the 30-meter telescope, in terms of the order of improvement that we're talking about here. And in fact, if you just want to talk about the gross size of the thing, this is roughly to scale. That's NICER on the ISS, and this is STROBE-X by comparison. And then we have a little Lego Mae Jemison scale to her height, and she was actually in the picture. So this is going to be a whoppingly large amount of collecting area compared to the state of the art in the field. And as such, we're going to be able to handle very high photon rates and very bright sources. There are three instruments that are going to be on board STROBE-X: the wide field monitor, which ranges from about 2 to 50 keV, the X-ray concentrator array, which is the souped up NICER bit of this. It's going to range from 0.2 to 12 keV, and the large area detector, which is sort of the loft portion of this, which is from about 2 to 30 keV. If you look at the effective area curves of these instruments, you can see that the two combined, the LAD and the XRCA, combined to produce the black line up on top there. And this is quite literally orders of magnitude improved over the sensitivity of most current instruments. And in fact, even when you evaluate it against something like the concept for the WFI instrument on board Athena, we're talking about something that is a substantial improvement over a broader bandpass. The shaded area in pink here, by the way, is roughly an approximation of the iron K region. So this is going to offer huge improvements in sensitivity in that area particularly, which is of interest for a variety of phenomena associated with compact objects. Just to give a brief overview of the instrumentation, the X-ray concentrator array, XRCA, is the scaled up version of NICER. It's got a focal length of 3 meters. It's pretty much high TRL as is, because as I said, the technology to build it already exists. But what it's offering through 10 units of the X-ray concentrator array is roughly 10 times the sensitivity that you're going to get with NICER. And it's got low background, high throughput, and it's got very sensitive timing capability, 100 nanoseconds, as a matter of fact. So this is a huge amount of effective area, over 2 meters at 1.5 keV, and it's got very sensitive timing resolution as well. The large area detector is based on SDDs, silicon drift detector concepts, and it's got a lightweight microcapillary plate collimator that was developed for the LOCKed mission, hence the heritage there. This is going to offer something of the order of 6 square meters of collecting area, roughly 10 times what RXTE was able to offer in the iron K band. So this is going to be a huge improvement for looking at science like sensitivity to QPOs, burst oscillations, other types of hard X-ray phenomena, in addition for all the science that we can do in the iron K band, looking at accretion and outflows and other sensitive indicators in that area. And of course, with a bandpass that extends up to 30 keV, it's going to be sensitive to the Compton hump as well, and non-thermal emission from the X-ray corona. So being able to help disentangle those two components in terms of the spectral curvature that they manifest in that energy range is going to be some very important STROBE-X science. Finally, the wide field monitor is going to be our big transient detector. And because we're going to have this in the same observatory that we have the other two instruments, they'll be able to talk to each other, and very quick repointing will be able to happen. This is also going to be responsive to alerts in the optical on a time scale of about 3 hours. So STROBE-X, which can slew at, I think the goal is 15 degrees per hour, is going to be a very agile observatory in terms of responding to transients, both self-alerts and alerts from other parts of the electromagnetic spectrum. The instantaneous view of the sky is about a third, about 4 steradians roughly, so it's getting an excellent look at things. And as I had said before, it's going to be about 15 times more sensitive than the all-sky monitor on board RXTE. I think the sensitivity the sensitivity limit instantaneously is 600 millicrabs. And if you observe over the course of a day, that goes down to 2 millicrabs for the sensitivity limit for this instrument. So triggering and autonomous repointing is going to be a big part of the science that's enabled by the WFM. So in terms of what this is going to do for the science that this observatory purports to explore, this is going to offer simultaneous broadband coverage of both the soft and the hard X-rays. So for something like X-ray binaries, for example, where you have a black hole in this case surrounded by an accretion disk, we know that these things, when they're bright and they're accreting, tend to have very prominent black body-ish thermal spectra, and also some non-thermal component from the corona or perhaps the base of a jet. Now, NICER has done a bang-up job looking at the soft thermal component of this so far, but being able to simultaneously observe both components is going to offer a huge advance in terms of understanding state changes in X-ray binaries, for example. And because this is going to be a very responsive, very flexible observatory, it's going to offer a wide variety of science that's really something applicable to the whole community. As most of you know, I think the probes are going to be primarily general observer-driven facilities. So it's important that we offer something for everybody, quite literally. So as I was saying, NICER has done an excellent job at looking at X-ray binaries. And this is a typical spectrum of MAXI J1820, which I think some of you have probably read about recently in the Nature paper I was referring to. But in 1 second, which is roughly the viscous time scale in a system like this, NICER gets an excellent spectrum of the thermal portion of that radiation. In 1/100th of a second, STROBE-X can do comparable signal to noise. So now we're talking about probing not just the viscous timescales of these systems, but something like the dynamical timescales of these systems. You can literally start making spectral movies of how these spectra evolve over times. So this just opens up a completely new ability to probe the time variability of these phenomena, state changes in X-ray binaries in particular. So you can see that the two instruments also combine to offer you a view not only of the thermal component, but also of the hard component as well. So if you recall the 3 science pillars that I mentioned at the beginning, one of the ones that I'm going to focus on, because it's mainly in my wheelhouse, is uniquely applying multiple techniques to constrain masses and spins of stellar and supermassive black holes. So when we measure spin, and the reason we care about measuring spin is because for stellar mass black holes, this can probe their natal conditions. We don't expect them to evolve significantly in mass and spin over their lives. For supermassive black holes, this probes how they form and grow. So whether accretion or mergers really play a more dominant role in the growth of black holes hosted in AGN. So there are 3 principal methods that can be brought to bear at the moment in terms of measuring spin for an isolated black hole system, something that's not merging and creating a LIGO signal, in other words. There is the continuum fitting method, which I've already referenced, and which most of you are probably familiar with, because I know Jack Steiner has given several excellent talks here on the topic. There's the reflection method, which I'll talk a little bit about myself. That's in the middle. And then there are these mysterious quasi-periodic observations that have been observed in another number of stellar mass black hole systems. These could potentially be due to kinks or warps in the innermost parts of the disk, and those would correspondingly have an effect on the spectral signatures that we see from the innermost parts of the disk. So those are 3 independent techniques that STROBE-X can bring to bear on these systems. And that's very important when you're talking about trying to break down systematic uncertainties for each method and use them to cross-calibrate with each other. We know that for a given system, of course, there is only 1 black hole spin. So if you're getting 3 different answers using 3 different methods, there is a problem. STROBE-X will allow us to address this. All the methods that we have for constraining black hole spin are predicated on the notion that there is this wonderful monotonic relationship between the innermost stable circular orbit in the accretion disk and the spin of a black hole. GR predicts this, and the plot on the left shows, for a Kerr spacetime, what we expect in terms of those numbers. For a non-spinning black hole, 0 on the x-axis, we know that the innermost stable circular orbit is fixed at 6 gravitational radii. If you spin up that black hole in the prograde direction to its maximum possible value, you bring that inner radius down to close to 1 gravitational radius. Whereas if you somehow wind up in a configuration where the black hole and accretion disk are rotating in opposite directions, frame dragging effects go in the opposite direction, pushing the ISCO out to about 9 gravitational radii. So for the continuum fitting method, as Jack has talked about a number of times, the way this works is basically you treat the disk as a modified black body, much like you would treat the radius of a star, and you determine the size of the hole in the middle, kind of the same way that you determine the size of the star. So basically, you're starting off with a system in which you have to know the mass, you have to know the distance, and you have to know the inclination angle to your line of sight fairly well in order to make this work. But provided that you know that, and you can get good X-ray luminosity measurements and temperature measurements through the models that you apply, you can then back out the inner disk radius. And we assume that that is the radius of the ISCO. If it's the radius of the ISCO, we can read out the black hole spin corresponding to that. So that's how this works for continuum fitting. And as I said before, STROBE-X is going to do a fantastic job at getting measurements that enable these type of spin calculations, these type of radius of the ISCO calculations, and will do so on dynamical timescales. So that means when we're talking about black hole binaries that are undergoing state changes, we can probe the nature of those changes over the timescales in which they happen, and we can do so with unprecedented sensitivity. So we anticipate that we can do this for roughly 50 to 100 stellar mass black holes with STROBE-X. As with any observatory, it's going to depend on how much time you want to devote to that science, but theoretically, this can be done for a whole lot of them. And as soon as you start getting orders of like 50 to 100 measurements, then you can start doing interesting distribution comparisons. So right now we're stuck at a couple of dozen. So this would be an enormous advance. Now for reflection, the way this usually works is, as I said, there's this nice monotonic relationship between the ISCO and the black hole spin. And if you look at spectral signatures, in particular emission lines from the accretion disk, the shape of those emission lines encodes information about where that ISCO is. The nice thing about the reflection method is that it doesn't rely on independently knowing the mass, the inclination, or the distance of these systems. None of those factors actually plays in. So this can be applied to both stellar and supermassive black holes with ease in approximately the same way. So the way this works is pretend that the disk is made up entirely of iron atoms. And here I choose iron because it's got a high fluorescence yield. It's quite abundant in these systems. And also it's got an energy in the rest frame of about 6.4 keV, meaning that it sticks up over the continuum pretty readily for systems that have a general power law shape of roughly, e to the -2, as AGN typically do. So if the disk is made entirely of iron atoms, and we're looking at a narrow annulus at, say, 400 gravitational radii, we would expect Doppler shifting to alter the profile of this line, and it would be doubly peaked. As you start to move in, say by a factor of 4, you notice that asymmetry begins to creep into the shape of the line. Moving in further, that asymmetry becomes increasingly pronounced. Finally, you notice that as you move in very close, within 10 gravitational radii of the hole, you start to drag the centroid of that line down to lower energies as well. And finally, in the case of a non-spinning black hole, 6 gravitational radii is as close as you can get before you plunge in. Once you get down to this radius, the emission from a narrow annulus around the hole is extremely broadened and skewed. Now, if you add up all of those annuli in the disk to make a composite line profile, you would see something like we see in the black there. And it turns out that because of the effects of both general and special relativity, the last stable orbit in the disk, which is approximate, per spin, can be linked very sensitively to how broad the red wing of that iron line profile is. Now, of course, when you're talking about the reflection spectrum as a whole, you're talking about not just the iron line, you're talking about other fluorescence lines that might be excited, and you're also talking about the Compton hump. So it's just an illustration on the left showing retrograde, non-spinning, and prograde configurations for the black hole and accretion disk. But what we see is that the appearance of these reflection features, particularly the broad iron line, but to a lesser degree also the Compton hump, are all affected by the black hole spin. So if you can sensitively isolate the reflection signatures in these spectra, pulling out the black hole spin is something that we can do. We now have models that can do this. So just as an example of what STROBE-X can bring to the table here, this is a 100 kilosecond simulation of an observation of a very popular AGN for measuring black hole spin, MCG6. And this is outstanding signal to noise in a typical time scale that's of the order of a third of what we would usually observe with something like Chandra XMM or New Star in order to get a good spin measurement for this object. So what this means is that you can actually break this down into even shorter time scales. In AGN, for example, we are often looking through kind of horizons of material along the line of sight to the black hole. There are clouds, there's obscuration, various different levels of ionization can be in the way, as well as column density. So looking through all this obscuring material can actually distort a spectrum in something like the way that you see distortions with the Compton hump and the broad iron line. So being able to separate out the absorption from the reflection is really the name of the game in AGN. And the bandpass of STROBE-X, as well as its sensitivity, allows us to probe that uniquely. We get the iron line and the Compton hump at once, and we also get them with enough sensitivity that you can break this down into much smaller time intervals over AGN typical variability cycles, say tens of kiloseconds, and you can see what is changing and when. And this allows you to break those modeling degeneracies between reflection and absorption. STROBE-X, we think, is capable of getting spins in roughly 100, even more, AGN using reflection modeling. So in this case, as I said, the reason we want to do this is because we like to probe growth mechanisms in AGN. Are they growing primarily by mergers? Or are they being driven by prolonged prograde accretion or even chaotic accretion from lots of different angles? We can probe that if we have an ensemble of spin measurements. Right now, these are current measurements here shown in the histogram at the bottom. We have roughly 36 black hole spin measurements. And that's pushing the limits of our current detectors to pretty much as high as they can go, considering that, as I mentioned before, the type of signal to noise that we need in order to do this science typically requires exposure times with instruments like XMM and New Star on the order of hundreds of kiloseconds. Getting that through attack is arduous. It's an expensive observation. And a lot of times you hear, well, you know, what's more, one more AGN. One more AGN isn't the goal. Getting 100 AGN or so is the goal, because then we can start looking at histograms like this and how they compare to histograms like this, which are from numerical simulations. Stuff that people like Marcia Voluntari have been pioneering for years. We can actually start probing with real observations, provided that we have enough sensitivity with something like STROBE-X. So this would be game-changing for measuring black hole spins with reflection modeling. And finally, as I said, you know, there are these mysterious QPOs. So far, they've only really been observed well in X-ray binaries. In principle, they could be observed in AGN as well. And no one is 100% sure exactly what the physical mechanism producing them is. There is a wide body of evidence suggesting that these could be due to warps or kinks, some sort of lens tearing precession in the inner part of the disk due to a misalignment from accretion, most likely. But in any case, if there is such a misalignment or a kink in the disk, as it rotates, you're going to see the spectral profile associated with emission from that region change correspondingly. And that will produce characteristic time signatures in the data known as these quasi-periodic observations. So STROBE-X is going to be, with its high throughput, its high collecting area, and its time sensitivity, the best instrument ever for probing QPOs and seeing what type of inferences we can make physically about the structure of the innermost disk based on these phenomena. So if we can measure spin using these three disparate techniques, and we can bounce those spins off of each other, we can compare and contrast, we can start breaking down some of the systematic uncertainties that are associated with each method. As I said, for a given system, if we're lucky enough to find a holy grail where all three measurements are possible, which would probably be in an X-ray binary, all three should yield the same answer. Right now, we're doing really well in terms of how, whoops, that did not go well. Let's see if I can share that again. Did PowerPoint die completely? No, that's not it.
Yeah.
I think it died. Sorry about that, folks. See if we can get that restarted.
We get to close and we start sharing.
Okay. Let's see. Where were we? QPOs. Excellent. Try this again. All right, QPOs. So if STROBE-X can get all three measurements and they all compare favorably, that's going to be a game changer. As I was saying, the continuum fitting and the iron line methods right now are aligning fairly well for a system of X-ray binaries, but there aren't that many points of comparison where we can get measurements with each technique for both. And I think at the moment, there's only one QPO spin that's been derived for an X-ray binary system. So being able to get all three would be huge. So as I alluded to earlier, spectral movies are also going to be popular. When you start probing smaller and smaller time cuts in these systems with excellent signal to noise, you can start truly making little flip books, or effectively movies, of what the spectra look like as these things evolve in dynamical time and viscous time scales. And this has just simply not been possible with current instrumentation. So things that have been percolating around in simulation world since the early 2000s are going to become realities with data in the next decade. X-ray reverberation is sort of another pioneer in terms of measuring masses and spins in AGN. And this is a timing technique. I know that for most people, images are easy to process. Spectra are slightly harder, but if you do it all the time, it's okay. Timing can be yet more complicated. So to break it down for you, in these systems, the way reflection and the way continuum fitting work is you have a disk that's emitting thermally, and for X-ray binaries, it's emitting thermally in the X-rays. You have a corona situated in some as yet unknown geometry, sandwiching the disk. And thermal X-rays from the disk interact with relativistically moving electrons in the corona. Some of them get Compton scattered, or shall I say inverse Compton scattered, back down onto the surface of the disk, exciting a series of emission lines, for which iron K alpha is the most prominent example. I already mentioned this for the reflection modeling piece, but because of the time delay involved, since you have a corona that's above a disk, there's going to be a distance delay and effectively a time delay imprinted on those photons that get reflected and ultimately come to the observatory. Because of that, if you were to look at the two light curves, the light curve of the continuum emission from the corona versus the light curve of the reflected iron K alpha line, that time delay for those photon arrival times would be imprinted on those two light curves. Fourier transforms tend to be a better way to pull out these types of things. So when we look at it in frequency space, do the math, we can actually plot that time lag on the y-axis here at the plot at the top versus energy. And it turns out that this is an excellent way of probing black hole spin as well. So this has been done, again, kind of pushing the limits of current limitation with XMM and with NuStar very well for a handful of sources. But a measurement, that can be made in 100 kiloseconds, a typical observing time for something like this XMM, can be done in 100 seconds with STROBE-X. So again, the sensitivity just opens new doors in terms of being able to collect enough photons to do this very photon intensive science in shorter amounts of time, probing smaller time scales involved. So if you want to actually look at it a little bit differently, STROBE-X is going to beat down the uncertainties associated with these detected lags between the continuum and the iron K photons. And it's going to beat them down by quite a lot, 1 to 2 orders of magnitude compared to present instrumentation. It's even going to do better than Athena, depending on when Athena flies. So right now, we're pretty much limited to measuring these iron K lags in a small handful of relatively low mass CFERs. STROBE-X, because of its ability to probe a variety of time cadences and its sensitivity, is going to open that up. It's going to allow us to probe a much larger range in black hole masses than we've been able to get to so far, and a much broader range in timescales for that matter as well. So this is going to unlock X-ray reverberation as well as X-ray spectral techniques for looking at black hole spin. So moving on briefly to touch on some other science topics that STROBE-X will shed light on. Obviously, black holes are not the only thing it's going to look at, although it will be a prime pillar of the science case. Neutron star equation of state. Obviously, this has been a holy grail for NICER for some time, and STROBE-X will do even better. So the current parameter space, the plot here on the right is showing a simulation where you've got the current constraints that we can establish on the mass radius relation in neutron stars, shown by the dashed line. The little dotted circles, these ellipses here, are 15 different posteriors that were set up for the simulation for STROBE-X around a distribution if we assume that the correct model is the black solid line there. STROBE-X is going to narrow the window of how well we can constrain the mass radius relationship in neutron stars significantly. So again, this is going to be a game changer for this type of science as well, which is highly reliant on having excellent broadband spectral sensitivity and very precise time resolution, which STROBE-X will be able to do. Burst oscillations, thermal surface emission, accretion powered pulsations, these are all going to be accessible to STROBE-X. So again, having multiple techniques helps you mitigate systematic errors when you're looking at a question like the neutron star equation of state as well. Rapid and extreme explosions are going to be part of the bread and butter of the STROBE-X science case, particularly with the wide field monitor acting in conjunction with the other two instruments. So some examples of the types of science that STROBE-X will excel in: gamma ray bursts, X-ray flashes, tidal disruption events, looking at electromagnetic counterparts for LIGO and eventually LISA detections, supernova shock breakouts, X-ray bursts, stellar flares, lots more. The wide field monitor is going to offer arc-minute localization of sources. As I said, it's got roughly a 4 steradian instantaneous field of view, and autonomous repointing is going to be very, very helpful in terms of following up X-ray triggers. It'll also have a sensitivity, as I mentioned, of roughly about 3 hours to repoint for an optical trigger from the ground. So that will be enormously helpful in terms of synergies with, Vera Rubin, with NGVLA, with all sorts of other phenomena that can be probed across the spectrum. So 300 eV spectral resolution is what the instrument will offer. But again, it's not so much the spectra from this instrument that we care about. It's the fact that it's catching things and enabling the rest of the instruments in the observatory and many others to slew to them quickly. Multi-messenger astrophysics, I already touched on this, but STROBE-X is going to probe a broad array of phenomena in this venue as well. Extreme mass ratio in spiral events, QPOs from merging supermassive black holes, which would be very exciting. Neutrino discoveries from blazars, for example, millisecond magnetars, merging neutron stars. These will all be areas that STROBE-X will excel in and have excellent synergies with across the multi-messenger and electromagnetic spectrum. So if your favorite part of science is not represented on here somewhere, come talk to me. It's probably somewhere in our white paper, and I just didn't have room to put it on the slide. But this is just to illustrate the fact that STROBE-X is going to appeal to a broad swath of the community. So in terms of the synergies, again, obviously the synergies with finding electromagnetic counterparts of gravitational wave sources are going to be huge. Who knows when Athena will fly at this point? However, we do have a microcalorimeter going up next year, CRISM. So that is going to be a very interesting pathfinder, I would say, for some aspects of STROBE-X science. You might say, okay, well, with CCD type resolution, how are you going to compare with the microcalorimeters of the world? The answer is we're not going to compare, we're going to complement. So whereas CRISM will excel with its microcalorimeter at pulling out narrow emission and absorption features, this is going to be excellent a priori knowledge for something like STROBE-X, which can then come along and using that information as a prior, isolate broad relativistic reflection signatures from the inner disk for absorption, for example. So in any case, STROBE-X is going to have a huge number of synergies with Rubin, with IceCube, with NGVLA, with Cherenkov detectors, with CRISM, of course. Hopefully it'll still be flying at the time, and eventually with Athena. So this is going to be a very important aspect of the panchromatic landscape of the next decade. Finally, we have a very diverse and active community. This just shows some of the locations of our science team members. We're all over the world. Everybody's been very enthusiastic. We have, I think, bi-weekly seminars at this point on a variety of science topics. I know those have been advertised in the head bulletin, so I encourage all of you to attend. I always learn something new every time. So those have been a lot of fun for me. But in terms of the leadership, we've got NRL, we've got Goddard, we've got Marshall, Texas Tech. We've got a broad array of scientists from all over the world. So it's a very active community, a very diverse community. We have a lot of early career researchers that are very keen to be involved with STROBE-X science, particularly because of its synergies with all of these other missions that I've mentioned. So if you're interested in becoming involved, contact me. Jack Steiner, sitting upstairs, is also a member of the STROBE-X science team and has given a seminar already, done some excellent work on simulations, but we have representatives here as well. So just to leave you guys with a few thoughts, STROBE-X is one of several probe mission concepts that's going in, but I would argue that it is the one best positioned to address time domain astronomy in the 2030s. It's got flexible scheduling, it's got fast timing capabilities, and it has revolutionary effective area of square meters across the bandpass, which is just simply unheard of in terms of current instrumentation. This will open up a wide array of science and serve a large community. Capitalizing on the type of technologies that have already been developed for NICER and LOFT, it's a high TRL mission, and it is ready to be built in the next decade. Happy to take your questions.
Any question from the audience? Yeah. Go.
Do you think, Laura, that the sensitivity will be enough some tighter constraints on corrections to general relativity?
It will. In fact, that science I didn't have a chance to get into, but the sensitivity is going to be ideally suited for looking at corrections to GR if they exist. As a matter of fact, yes.
From the reflection method or from the time lapse?
Primarily, I think the time lags will be the best suited for that, but potentially also the reflection. The thing I didn't mention, and probably those of you who know the typical fluxes of AGN can do the math in your head. The LAD is going to be something that's a bit more background dominated for the AGN, not a problem for the X-ray binaries because they're so bright. But the XRCA is going to be more of a workhorse for the AGN. For the LAD, we're going to have to understand the background fairly well, but it'll still be a tremendous asset. Yeah. Scott.
So this is a slightly different kind of question. In the decadal, they also talked about a separate call for time domain science.
They did.
Is there any idea whether that is the same size cost gap as the probe, or is it just completely unknown at this point?
That's a good question. I confess I don't know the answer. Randall, do you have any insight on that?
The only rumors that I've heard, and they're rumors, is that headquarters is thinking about it being somewhat smaller cost cap, but they don't have the money identified for it yet. So it might be more $500 million class rather than billion class.
Mhm.
It's also not clear if they're going to put a check mark next to that based on, say, selecting STAR-X or UBEX from a mid-X. The decadal says that headquarters is in charge of deciding where checkboxes go.
Indeed. Fair point. Yes.
Yeah, very nice. Question regarding to the measurement of the black hole speed using the East Core radius actually. So I want to know if there's any chance that some of the radio data can be useful, because for instance from the Event Horizon Telescope we have a very precise measurement of the photon range, basically the radio if you under some certain conditions and so on. So would that be possible to combine those to have a little bit unbiased or more unbiased measurement?
It would, theoretically, yes. The only problem, well, it's not even a problem, it's a feature of the Event Horizon Telescope is that, of course, you're somewhat limited in the objects you can do this for at the moment.
Yes, yeah.
So in theory, for those two, yes, we can. We don't actually have good X-ray information on reflection in Sagittarius A star at the moment because, thankfully for us, our black hole is a bit of a picky eater. So we don't have, a robust, actively accreting nucleus at the heart of our galaxy with which to really probe the black hole spin through the methods that I mentioned. M87, who knows? We don't have any good X-ray data from that either at the moment, but sometimes things change. So, who knows what the future will bring. At the moment, though, theoretically, if we were to get simultaneous data from the Event Horizon Telescope and these X-ray techniques for the same object, theoretically, it would be possible. So maybe this is like an NGEHT type situation.
Yeah, but the next generation of the Event Horizon Telescope can go up to thousands of different sources.
Exactly. Yes.
The communication between X-ray and radio will be much stronger.
Yeah, primarily the complementarity at the moment between X-ray and radio probes of black hole spin has been through looking at jet power with the radio, actually. Ruth Daly, who's at Penn State, has been doing some work on this for several years, trying to measure jet power and assuming a Blandford's-Nyack mechanism, tying the spin of the black hole to the jet production. She's been able to infer black hole spin constraints for several hundred radio loud AGN, I believe. So the constraints aren't as precise as what we're getting with the X-ray modeling. But as you're saying, something like NGEHT might be able to bring that technique to bear in the situation. Pepe.
Yeah, it's a nice mission. If it happens, what would be the CFA involvement at that time?
Well, right now there is no formal CFA involvement. So as I said, Paul Ray is leading this out of NRL, and there's, people at Marshall, people at Goddard, and people at Texas Tech who have leadership roles in the mission. I'm fortunate to be on the steering committee because I was asked, but the CFA as an institution currently does not have any involvement with STROBE-X on a formal or funded level. So if it goes forward, I'm hopeful that that will change.
Yeah, we put that data,
We have many capabilities here that would be very complementary, I think.
Sorry, really broad question. What are the downlink rates needed for this? I mean, is it feasible?
It is feasible. I have the downlink rates, I think, in the white paper. I don't have them with me at present. But yes, they have done that calculation and the downlink is eminently feasible.
I mean, is it a low Earth orbit?
It is a low Earth orbit, yes. 10 degrees inclination, Leo. Yes, but they have done the work on that. So I can tell you with very high confidence that yes, that is feasible. They have looked. Randall.
I realize I've given talks like this, but I just never really knew the answer to the prograde, retrograde disk motion. Does the disk itself have any large phenomenological aspect of that, or are we really measuring the orbits of the individual particles that are being reflected off of things? So does it, if you had just one particle rotating around, and a photon came in and reflected off of it, would you still get the shifting prograde or retrograde, or does it need to be a disk phenomenon in order to give you the shift?
Well, in theory, you could do a one-on-one calculation, and in fact, that's what ray tracing codes essentially do. The little cartoon that I showed you assumed a narrow annulus, so essentially a one gravitational unit wide ring. But yes, in theory, one-to-one calculations are possible. That's what ray tracing codes typically do.
So the frame dragging is purely the black hole. There's no aspect of the disk itself.
Yes, the frame dragging is just set by GR in the space-time. The disk happens to be sitting in it.
That's why I think it would work for testing GR.
Yes. Any other questions?
Amy, can you see any question online?
Yeah, we have a hand from Brandon Allen.
Go ahead, please.
Oh, yeah. Hi. So you were saying that you were able to do follow-ups autonomously, or you're planning on being able to do follow-up autonomously from your wide field monitor. What's the slew time that they're trying to target? I think you said 4 hours from the ground, but I didn't hear a number from onboard processing.
3 hours from the ground. On board, I think it's a matter of seconds, actually, to begin a slew.
To begin, but what's the hope?
So the slew rate, the rate as a goal, I think the requirement is 5 degrees. The goal is 15 degrees per hour.
Okay, 15 degrees in a few seconds, you're saying?
No, not 15 degrees in a few seconds.
That's
15
yeah, impressive.
15 degrees in a few seconds would be problematic, I think. But
Right. I think so too. So it's something on the order of a couple minutes, I guess, at minimum.
yeah, I literally meant from the time the WFM would detect a trigger to its time to communicate that to the other instruments and initiate repointing.
Right, and then repoint, like you would want to get to the source within how much time? Like from the time to detection to the time. Sorry.
Probably a couple, well, depending on how far it has to go, a couple of hours. 15 degrees per hour is the target slew goal.
Oh, 15 degrees per hour. Okay, sorry. That's I didn't quite catch that. Now I got it. Thank you so much.
Definitely not per second, but per hour. Yes.
Right.
Amy, any more question online?
I don't see any other hands or anything written in the chat.
Oh, okay. So in this case, let's thank
Right.
my Laura for joining.